Hello everyone. We've gotten to the phase now where we've seen feed-forward neural networks and we understand how to interpret them geometrically, so we could build up our own neural networks if we kind of know what regions of the space that we need to carve out. But that's a tedious process and we would like to automate that process. I showed you how to do that in Torch, but I want to start to demystify what's going on under the hood. And so I want to manually figure out how to best tweak the parameters of my feed-forward neural networks, or I'll call them MLPs for short, multi-layer perceptrons. I want to figure out how to tweak the weights and the biases of these automatically to make the fit of my system better. So let me unpack each of those parts of it first. I have these functions that are going to come in handy, which I've talked about before. One of them is the logistic function. The other one is the leaky ReLU. These are activation functions that I'll eventually apply element-wise to outputs of different layers in the multi-layer perceptron. But first, let me talk about how to represent each layer in the network. So let's suppose that we had an example where our data was in 2 dimensions. So here's the data. And I'm going to do binary classification problem. So I have all my examples with a label of 1 in this circle here and this circle here, and the rest of them should get a label of 0. So my input here has 2 coordinates, has 2 dimensions. And so what I'll do is I'll have this list of layers. Each layer is a list of the weights, the biases, and a function handle to activation function that we're going to use. So as an example, perhaps in this first layer what I'll do is I'll take an input of 2 dimensions and I will output to 5 dimensions. And so that'll be like using 5 neurons in the first layer. And so if you remember, the way that works is I'm going to set up a matrix, and I'll randomly initialize the weights here. But I'll set up a matrix with 5 outputs. So I have that in this variable here because I might play with this a little bit later. 5 outputs takes in 2 inputs. Okay, so it has that matrix of weights is going to have 5 rows and 2 columns. I also need a matrix of biases. So I'm randomly initializing these. The matrix of biases is going to have 5 rows and 1 column. So we just need 1 bias for each neuron in the output. And then I'll use a leaky ReLU as my activation for this first layer here. All right, so that's my first layer. And then maybe for now I'll top it off with just one more layer. It takes... Sorry, that's my dog here. He's a beagle. He does reverse sneezing, which is very funny and cute, but also a bit loud. Anyway, so we have we've inputted 2 dimensions to the first layer. That layer outputs 5 dimensions. What we'll do is we'll take those 5 dimensions then down to 1 dimension. And so what I'll do is I'll output 1 dimension, input 5 dimensions, and so then I just need 1 bias on the way out. And actually in the last layer, what I'm trying to do is make a function whose input is an x and y coordinate, and whose output is just a single number between 0 and 1. I would like the number to be 0 if I'm actually in that class, and I would like the number to be 1 if I'm in that 1 class. So what I'll do is I'll actually, in the last layers, the output of the last layer, my activation function will be the logistic function, which squashes things between 0 and 1. All right, so I'll say the logistic function as the last one. Okay, it's worth probably drawing this out just to make sure we're on the same page. So like I said, the input has 2 coordinates, x and y. And in my inner layer here, I'm doing 5 units. So I want the output of my first layer here to be 5-dimensional. So that means that I need 5 neurons. And so, like I said, this is what's called a multilayer perceptron. What it means is each perceptron, the output of each layer feeds into the input of each perceptron in the next layer. So I need to take all the x's and feed them as inputs to the next layer. Then I need to take all the y's and feed those as inputs to the next layer. So the first layer looks like this. And actually in this MLP I only have one hidden layer, because then I immediately just top it off with a single perceptron at the end, which takes 5 inputs from those 5 outputs on the previous layer, and which then just has a single output, which is what I'm going to use as the output of my overall function here. And that's what I'm going to compare to what it's supposed to be here. Okay, so the first thing I'll do is let me create a method to evaluate the function. So to take the inputs and to propagate them through each layer and eventually return the output. So I have a skeleton for this here. It takes as a parameter the list of layers, which is a list of lists, which each has the weights, the bias, and the function to apply element-wise. And then which takes the inputs to apply it to. So normally the inputs are, the convention is that a data matrix has all of the different data elements along the rows and the dimensions along the columns. But actually here, the way that we've been setting up the weights matrix, we multiply by the weights matrix on the left. So there we interpret each data point as a column vector. So the first thing I do is I take the transpose. Okay, so I switch the rows for the columns. Whatever. But then it's actually pretty straightforward. To do this, what I do is I'm just going to loop through each layer in succession from left to right. So I'll say, okay, for the, I know I've got a weight, I've got a bias matrix, and I got my function to apply. So I'll say go through each of those in the layers. And then I will just apply that. So I'll say y is equal to w dot y. So, okay, so the y from the last layer. So this starts off as the input, but it's going to get crunched through successive layers. The one from the last layer, send it through all the weights, do the dot product with each weight, set of weight vectors for each neuron. Then add each bias element-wise to each neuron. And then finally apply the nonlinear function, the nonlinear activation to each element of the output. So there's actually a lot going on in this line. It's kind of cool though, because in Python and NumPy, we can write it almost as if we would write the math equation. But this is a matrix multiplication here, plus element-wise addition of the bias, and then doing element-wise evaluation of the function. So there's actually a lot happening under there under the hood. It looks quite nice in Python, and I can just return the result when I'm finished. So first, let's just see if that worked. So what I'll do is I'll apply. I'll say my y estimate is n forward, the layers, and my inputs. And what I'll do is I will plot what this gives me. Let's see, didn't like that. What did it not like about this? List indices must be integers or slices, not tuple. Where am I using a tuple index here? Let's see. Oh, well, I just forgot comma at the end of this. Okay. Anyway, there we have it. So we randomly initialize the weights here. If I use a different seed, it'll get a slightly different one. So here, seed of 1 looks a little bit different. So we randomly initialize the weight, so we shouldn't really expect this to match up at all with our output here, and it really doesn't. So we have to do some more work to actually get this to match up. But first of all, though, maybe we should figure out a way to measure how well we're doing, right? So I've talked about loss functions before. Loss functions are ways of measuring how far our output is from what we want it to be. And I've shown you a variety of loss functions. But let's just talk about a simple one here, which is, well, I can look at each data point and sum up the square differences between the output. and what we want the output to be. So I have a little skeleton here for the loss function. So I tell you what the output's supposed to be. And let's see what the output actually is. So if I call the method, so I'll say ys equals nn forward layers x's. So now I have what my output was supposed to be, and I have what my estimated output actually is. And what I'm going to do is just sum up the square differences between the two. So this will do an element-wise difference between each output. I will square them and then sum them all up. And so let's see what it is. If I call this method down here, and let's say I make the title of this be what the loss is. So let's call it loss. Okay, the loss starts off pretty high at about 80. So summing up over these 200 examples, my average loss is almost 0.5. So that's pretty high. So now what we need to figure out is, okay, how are we going to, I randomly initialize these weights, but how am I going to tweak them automatically so that I get a better answer? So I have freedom to change any of the weights and any of the biases in the layers. I could also decide to use different activation functions, but once I've initialized this, I'm going to keep the activation functions fixed, and I'm just going to change the weights. All right? So here's where we're going to do what I call the lazy calc derivative. So it's if you are in a calculus class and you don't actually want to learn any of the rules for derivatives of functions, but you want to do kind of an approximation of a derivative. So we know that the derivative of a function it's really the limit as h approaches 0 of f of x plus h minus f of x all over h, right? So it's actually a limit, and normally you'd have to evaluate that limit or come up with rules to shortcut around it. But let's say we don't want to take limits. Well, what we're going to do is just choose a very small h. So approximation is just choose a very small h and just evaluate this equation. So add a little bit to the input, subtract it, and then divide by h. And that gives you, it's just a rise over run of what's called the secant approximation. All right? So this is what I want to do, actually, to my loss function to figure out the derivative with respect to each weight and each bias. So I want to figure out so I want to estimate the derivative of the loss function with respect to each weight and each bias. And so what I'm going to do is loop through all of the weights and all of the biases, and I'm going to twiddle each weight and each bias in turn, and I'm going to see how does my loss change. So first I'll just compute the loss beforehand. So this is like, in the above equation, this would be like f of x, where x is all of my weights and biases. And now what I'm going to do is I'm going to initialize a matrix or a bunch of matrices for the weights. So I'll say w's deriv equals w for w blah blah in layers. Actually, let me see 0 times w. So I'm going to initialize a matrix that has the same dimensions as my weights matrix for all the layers. And I'm going to initialize also a bias matrix that's much the same. And so here I want to compute an estimate of the derivative of the loss function with respect to each of these variables. So I'm going to create a space to hold that derivative for each variable. So now I'll just go through and follow my plan to do a secant approximation. So I'll say for I in range length of layers. So I'll go through each layer. I'll pull out the weight and the bias. I actually don't need the function for this part of it. I'll pull out the weight and the bias from that layer. And now what I'll do is I'll loop through every element of the weights matrix. So I'll say w.shape0 for call in range w.shape1. And I will first remember what is the value now. So I'll say, okay, w at row, call. And now I'm going to change that value a little bit. So I'm going to go into that matrix. I'm going to say w row call plus equals h. So let me twiddle this weight a little bit. I'm going to keep all the other weights fixed. I just want to know what is the impact of this single weight in this layer that I'm looking at right now. And if I find that increasing that weight increases the loss, then that's a bad move. I actually want to decrease the weight. But if I find out that increasing the rate decreases the loss, that's great. Let me go ahead and increase that weight. Okay, so I want to look at just each weight in isolation and see what the effect is on the loss function. So what I'll do now is I'll compute the resulting loss. So I'll call that loss after I said that's get loss x's, y's layers. And now I'm just going to look at my secant equation. So I'm going to say, okay, let me remember. Here's what the derivative is. So the derivative of this particular weight, my approximation is the loss after minus what the loss was before over h. Okay. Now I'll go ahead and reset what that weight was to what it was before. Okay, so I twiddle it a little bit, see what happens. Now put it back to what it was. And I'll do the same thing for the biases. So there's only one bias for each output neuron, so I don't need that inner loop, but I'll say, okay, for each bias, let me take it out. Let me remember what it was, but let me now change it. Let me twiddle it a little bit. I'll compute what the loss after is. And then I'll say that my b's, I'll remember that the derivative of this particular bias at this layer was the loss after, again, my secant approximation. And then I'll reset the bias to what it was before, put it back. All right, so these are going to be all my derivatives. I'll return them. At this point, I better make sure this code runs. So let me just call this real quick and see what I get. So if I make a cell here, I'll say w's deriv, b's deriv equals. Get the derivatives. Okay, that's great. And if I look at one of those, I see that it has as many elements as there were elements in the weights. So this tells me, for example, that the first weight in my first layer, if I increase that weight, then the loss is going to go up. But if I increase my second weight, that the loss is going to go down. So what we can do, actually, is go down in here into a loop where we go through a bunch of epochs. We compute the derivatives, and then what we do is move against the derivatives by some learning rate, right? So this is just like what we've been doing before. Once we have the estimate of the derivative of the loss function with respect to each parameter, we're going to move the parameters against the derivative. So the derivative tells us the direction of steepest ascent of the loss function. How can we most quickly go up? If we go against that, we're going to go in the direction of steepest descent. So let me loop through all the layers, and then I'll say layers. All right, so the weights plus equals, or I guess I'll say minus equals alpha times the derivative. And then I'll say that the bias, which is the second element, minus equals alpha times b's derivative I. Okay, so that should be how we do the update. And now what I'm going to do is compute the loss, keep track of the loss, and every 1,000 epochs, I'm going to plot how this is doing. I'm going to show, the result. Okay, so let's see. And I guess maybe I'll print the loss too to see how things are going. So let's run this and see how it does. So I run this, the loss starts off at 80, and now the loss is slowly going down. And that's great. The loss has gone down to about 11. Now it's going down even further. And here's our final result. So this carved out the space pretty nicely. And it's not perfect, but it's a heck of a lot better than it was when we started. So if I look at the progression here, this is kind of the initial random weights that I had. And then as we keep taking steps, we eventually converge towards this thing, which seems to fit the data a lot better. So we can also look at what happens when we add more neurons in this inner layer. So let's go maybe from 5 to 10 neurons. Okay, the loss starts off at about 75 this time. Let's look at the progression, see if we do any better. Okay, so we actually more quickly in this case we're able to go down to a lower loss. If I show you what's happening here, it's still running, but I can start to show the output. Okay, so somehow with these additional neurons, we were able to kind of carve out a more precise partition here. And if we think back to what we know about how this works geometrically, then that should make sense. More neurons in the hidden layer means that we can have more basically line segments here in the regions that we carve out. And so that's cool. Let's see what happens if I add another layer. Maybe not just one hidden layer, but maybe I'll add something else. So maybe I'll say, okay, the output of the first hidden layer has 5 neurons. Maybe I will make, so the input to that layer has to have 5, but maybe I'll make the output of that, I don't know, be 10 or something. Oh, I'm sorry, I'd already changed the input to be 10. Okay. I don't know, but maybe this hidden layer outputs 5 things. And I'll use a leaky ReLU again. So then the last one's going to take as input 5 things, and it's going to output 1. Oh, I keep forgetting to put my comma here. Okay. Anyways, so that's that. Let's see how that does. Okay, so we got down to a loss of 5 before with 10 neurons and 1 hidden layer. How does it do if we have 10 neurons and 1 hidden layer, but we follow it by another hidden layer? Let's see. So it's going to take longer, and this is part of why we don't. Okay, this technique seems to be working pretty well, but we're not actually going to use this moving forward because it takes too long. Because we have to loop through and we have to keep, for every single weight, we have to evaluate the loss function from scratch on all the examples. That's not very efficient. We're gonna figure out a much more efficient way to compute the derivatives. But anyway, let's look. This is in the middle of doing something. This is what I had before at this stage, and we're about to get to what do I have now at this stage. Okay, so same number of iterations. I got even better. So somehow, yeah, so going wider and deeper can help with the caveat that if you have enough, it's important that you have enough data for that to work. Otherwise, the training can get a little bit crazy. So this is how we did with 2 hidden layers and 10 neurons in the first one. So there are these things called universal approximation theorems that tell us that if you have a network with a single hidden layer but enough neurons, you can approximate any function. And there's other versions that say if you go deep enough, then you can approximate any function. So anyway, here's what we learned with the lazy calc derivative method. So kind of amazing. We didn't actually have to think carefully at all about this nasty function and how to take the derivatives. We were able to just twiddle our individual components and estimate them. Okay, but I'm going to start talking about how to use the actual derivatives because, like I said, this is too slow. But I hope that this made it clear what the parameters are that we're able to tweak and what the result can be on our final output. So maybe just to really nail that point home, I'll show you. So if I print out the layers here, this is what the weights are at the end in the first layer. And then this is what the weights are on the second layer and so on and so forth. If I were to start over, just to show you how much the weights have changed. So I'm using the same seed, so I'm going to get the same result. So the weights changed quite a bit. Okay, maybe this one not as much. That one went down from 0.65 to 0.5. But you can see some of the other weights change a lot more. This one started off as negative 0.7, but it ended up at a negative 0.2. This one started off at negative 0.1, but it ended up at negative 1. So anyway, just to show you, the weights have changed a lot. Okay, good. But let's continue on and talk about more rigorous ways of doing this, which will actually lead to faster algorithms.